Yes, thank you, Aisha, but the collision theory is quite difficult. Exam just around the corner. I need to study. Let's start with chapter 1, chemical kinetics. I can't understand a thing. I need your help.
Help! Aisha, come to the rescue! What's wrong, Yasmin?
I need to study for upcoming examination, but I don't understand this topic.
Oh, easy peasy, Yasmin. I can help you. Okay, Yasmin, did you understand what I explained just now?
Yes, thank you, Aisha, but the collision theory is quite difficult to me.
Okay, let me explain to you, okay? The collision theory is
used to predict the rates of chemical reactions, particularly for gases. The collision theory is based on the assumption that for a reaction to occur, it is necessary for the reactive species, atoms or molecules, to come together or collide with one another.
then
What is collision theory and how does it relate to the reaction rate? The collision theory says that chemical reactions only occur if there are collisions of the right energy levels between molecules and atoms. It follows that if the molecules collide more often, that this will increase the rate of reaction.
yes.
What factors affect collision theory? Reactions occur when two reactant molecules effectively collide, each having minimum energy and correct orientation. Reactant concentration, the physical states of the reactants and surface area, temperature, and the presence of a catalyst are the four main factors that affect reaction rate.
Anis, did you know there was an accident in front of our campus yesterday?
I heard about it. Is it so bad?
It's quite bad.
By the way, where are you going?
I'm going to meet Aisha and Yasmin.
Me too. Let's go.
Let's go.
Aisha, Yasmin, did you know that there is a car crash in front of our campus yesterday?
What?
It was really bad. There is a collision between two cars. Both of it looks like a scrap of tin after the damage. It was very terrible.
Seriously?
Yeah, seriously.
Aha! I got an idea on how to explain the collision theory to you.
How?
Okay, let me explain.
Gasoline has approximately 56 megajoules of chemical energy per liter, which is more energy than you get from exploding the same amount of TNT and is enough to power a toaster for a full day. Cars work by burning gasoline to convert that chemical energy into the kinetic energy of motion of the car, though almost 80% of it is lost as heat in the engine. Still, 20% of 56 million joules is a lot of joules. To give a direct sense of gas to car conversion, it takes about 5 teaspoons of gas to accelerate a 2-ton car car to 60 kilometers per hour, and about a third of a cup more for every additional minute you want to keep it going at that speed. That might not sound like a lot of fuel, but the energy of a car moving 60 kilometers per hour is equivalent to dropping an elephant, or Stegosaurus, from the top of a 3-story building. And in order for the car to stop, all that energy has to go somewhere. If the brakes do the stopping, they dissipate the energy by heating up. Or in the case of a collision, energy is dissipated by the bending and crumpling of metal in the outer areas of the car. And just like how smooth braking is nicer than a quick, jerky stop, cars are carefully designed to crumple when they crash, in a way that lengthens the duration of the impact so that stopping requires less intense acceleration. Lots of acceleration over a very short time is not good for soft human brains and organs. However, people don't like driving cars with Pinocchio-length noses, so most cars only have around 50 centimeters of crushable space in which to dissipate the energy equivalent of our falling stegosaur. That means that while crumpling, they need to maintain a resistive force of about a quarter of the thrust of the Space Shuttle main engine. Over half of the controlled crumpling work is done by a pair of steel rails connecting the front bumper to the body, which bend and deform to absorb energy and slow the car. Most, and in ideal circumstances all, of the rest of the energy is absorbed by the deformation of other pieces of structural metal throughout the front of the car. This meticulously engineered destruction allows a crashing car to decelerate at a high, but reasonable and constant rate, just slightly over the acceleration experienced by fighter pilots or astronauts in centrifuge training. As comparison, if cars were super rigid, like they were before the 1950s, and didn't crumple, they would stop so fast that they would undergo acceleration 15 times what fighter pilots experience in training, which is definitely not good for your internal organs. Thankfully, engineers have learned to make cars with crunchy crumple zones surrounding a rigid safety cell, because fully rigid cars are not good for fighter pilots or anyone else. Except maybe robots.
Application of collision theory. Example of collision theory: car collision with wall. Less injuries than a head-on collision between two moving vehicles. Consider car A collides with static, unbreakable wall. Begins with car A traveling with velocity v and with velocity o. The car is set first in the direction of the wall, but the wall exerts equal force back on the car. This occurs first, which causes cars to curling up during collision. Since the wall doesn't break or move at all, the full force of the car into the wall has to go somewhere. Car collision with car. More injuries than car collision with wall. Car A collide with car B. Different force consideration. Car A and car B are complete mirrors of each other. They will collide with each other going at precisely the same speed, but opposite directions. From law of momentum, know that they must both come to rest. The mass is the same.
And lastly,
From cars to particle. At the quantum level of particles, energy and matter can basically swap between states. The physics of a car collision will never, no matter how energetic, emit a completely new car. The only force that acts on the car is the sudden deceleration from v to o velocity in a brief period of time due to the collision with another object. However, when viewing the total system, the collision in case B releases twice as much energy as the case A collision. It's louder, hotter, and likely messier. The particle accelerated beams get more energy out of the collision if the particles are going in opposite directions, but they get more energy out of the total system.
Yes, and bye. Wait.
They're red, they're white, they're brown. They get that way underground. There can't be much to do. So now they have blue ones too. We don't care what they look like, we'll eat them any way they can fit on our plate. every way we can conjure to heat them. We're delighted and think they're just great. Potato, 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 potato. Sometimes we ditch the skin to eat what it's holding in. Sometimes we'd rather please have just the outside with cheese. They have eyes, but they do not have faces. I don't know if their feelings get hurt by just hanging around in dark places where they only can stare at the dirt. Potato, potato, potato.